Counting. It sounds easy, right? You just list things. So if you want to count the number of balls, well, you just list them. 1, 2, and 3. But in mathematics, we don't always want to list, especially when there are too many options. That's where counting rules come in. They help us figure out how many elements are in a set without having to list all of them. Let's look at two common rules. First, the product rule. If you make a sequence of choices like choosing a shirt, then pants, then shoes, and each choice has a fixed number of options, you multiply the options together. So for example, if you have 3 options of shirts, 4 options of pants, and 2 options of shoes, then you have 3 times 4 times 2, 24 possible outfits. Then there's the sum rule. If you have disjoint options, you just add. If a password, for example, is either 6, 7, or 8 characters long, you add the counts for each case. So we will have X possible passwords with 6 characters, Y with 7, and Z with 8. The total number of possible passwords is X plus Y plus Z. This is the sum rule. Now here's the real insight. We often want to count a set that's hard to work with. It's hard to count. What we do then is we find another set that's easier to count, and we will actually count one by counting another as long as both sets are the same size. This is crucial. And how do we know that they are the same size? We build a bijection, a perfect pairing between elements of the two sets. So if there's a bijection between, let's say, A and B, then we can count A by counting B. Let's try an example. How many groups of 3 students can you make from a class of 10? That's not easy to count directly, right? But here's a trick. Imagine that each student is a position in a 10-bit string. If a student is in the group, we put a 1. If not, we put a 0. So for example, the group 2, 5, and 9. This becomes the bit string 0, 1, 0, 0, 1, 0, 0, 0, 1, 0. So we have students 2, 5, and 9 represented as 1s in this bit string. What's important to notice here is that every group of 3 students gives a unique 10-bit string with 3 1s, and every such bit string gives a unique group. That's a bijection. For every group, you have a unique 10-bit string, and for every 10-bit string, you have a unique group. Next, we just count how many 10-bit strings have exactly 3 1s, and that's a known formula, which is 10 choose 3, which is equal to 120. So instead of counting student groups directly, we counted something easier but equivalent. And that's what a counting rule really is. It's not just a formula, it's a strategy. Find a simpler set, prove there's a bijection, and do the math.